everybody. I'm Scott McLeod. I'm Director of Innovation for Prairie Lakes Area Education Agency.
And I'm Mike Anderson, an Instructional Technology Consultant with Prairie Lakes Area Education.
We do a lot of different things. We work on learning and teaching and leadership and technology.
Do a lot with STEM. That's why we're here.
That's right. Prairie Lakes AEA is a regional ed service agency. We serve about 45 school districts in Iowa and about a dozen private schools. There are 8 or 9 AEAs, as we call them, across the state. If you're familiar with other states, it's like a BOCES in New York or a CESA in Wisconsin.
Right.
Okay, so we're going to talk about some elementary STEM activities. You'll notice that we filmed on multiple days, and so we, our hair may change or our clothes or whatever. That's just part of how it goes.
Yep.
Okay, so this is a STEAM conference, not a STEM conference, but
Right.
neither Mike nor I are artists, nor do we have an art background. But there's lots of sort of different things that you can do around the activities that we're going to show you. So we're going to be talking mostly about maybe more traditional STEM stuff, but we've got some opportunities to extend around the edges and do some interesting things, right?
Right. And these activities we're doing, these are not the cookbook labs we did when we were in elementary school. Right. They're wide open for creativity, just like today's. We're doing thrust wars, and we give them some materials, and we give them a couple parameters, and then it's up to them to construct a vehicle. There isn't a prescribed method or a prescribed look to it.
Right, so we're trying to foster some divergent thinking, some
Right.
creativity, some innovation. You have to make lots of design decisions along the way, and some of that is engineering and some of that is art.
Right.
There are opportunities, for example, I think about like some of the rockets that they make to make their things, sort of more aesthetically pleasing, but also functional.
Right. Yep.
You can build in some writing around this. You can have them tell stories. You could do design sketches up front.
Can have them kind of chronicle their journey with video, with photos, and create a photo story at the end.
Right, so like Mike and I have been sort of doing the audio and video and photography for this, but there's no reason the kids couldn't do any of that.
No.
And then those of you who are, have a stronger arts background than we do, I'm sure you could come up with lots of other creative ways to sort of wrap around sort of what are at their core STEM activities and turn them into more STEAM activities. So with the caveat that, again, our A background is a little weak compared to the rest of the STEAM acronym, hopefully you'll find at least some of what we talk about here today interesting.
Right.
All right, so Mike, we're taking a staged approach with kids, right?
Right.
Which means that we won't start them off with something too complex. They got to learn the robot. They got to learn sort of how it works.
Yep.
So what are initial tasks for kids with these robots?
Well, depending on the age of the kids, we could have them engineer the robot and construct it, right? So on the front here we have a touch sensor. They'd have to figure out how to put that touch sensor on. They also have to think about, if it's a touch sensor, it needs to be out in front so that it'll be the first thing that runs with the object.
Okay.
Okay, and then in the programming, younger kids might not be able to handle the programming, older kids can, so we have to kind of figure out where our students are at and if they can do the programming.
Okay, so depending on the age group, you might hand them a robot that was more assembled or that the programming code was already built in.
Right.
Older
Right.
kids, they have more flexibility
Exactly.
to build themselves. Okay, got it. All right, so what would be our initial task that we would give the kids?
So the task we're going to do here is just to have the robot go straight, and then using this sensor on the front, the touch sensor, when that runs into the object, it's going to, based on the program, it's going to tell the robot to stop moving.
Okay, what we're striving here is we're striving for a quick early win for kids
Exactly.
so they can get the basics of how to make the robot move and stop.
Yep.
Okay, got it. All right, and a successful run, let's show one of those
Let's
just for
see
fun.
what that looks like. Roll the weight.
This is science in action, folks.
Yep. Sometimes it misses the box. Not this time, though.
Success.
Yay!
Okay, so now we're on round 2 where we're asking the kids to do something a little more complex. So Mike, what do we got going on now?
Okay, so now they have to program the robot to go the distance. So there are no sensors involved. So they need to program the robot to go the distance, and there's several ways to do that. And we're using rotations. So they had to figure out how far it is the distance or the robot's going to travel. And then they also have to figure out how far around is it for one rotation. And of course that can be different depending on what wheels you're using. Okay, so for these wheels they'd have to measure the circumference around. Okay, and then divide, and that's how many rotations they have to program into the robot, so it'll go that distance. So
Okay,
let's see.
so now would we have them just measure around the wheel, or could we do something like calculated from the diameter or
Right. So
the
again,
radius?
depending on the age of the kids and what content that they're going to interact with in math, you could have them use the formula. You could have them just measure around. There's a number of ways to do that.
Okay, so lots of ways to pull math into this.
Yes.
Okay, all right, and then the goal is to get them to stop at the other tape line.
Right.
Okay,
Ready?
yeah. We're veering left.
Yes.
Sweet. All right, so we've done our straight track, and now what we're trying to do is we're trying to teach kids some next steps in coding and programming, right?
Right.
So what's the next task?
So we've gone straight now. We're going to turn 90 degrees. And to do that, we're going to use the color sensor. So on the front of the robot here, the color sensor is attached, it's looking downward. And we set it so that when it sees white, it'll move to the next block in the program. And in this case, it's just a stop block.
Okay, and then once it hits the cross tape there, it's going to turn 90 degrees, and then it's going to...
It's going to stop for a second and then move on to the next block, which is
Right.
straight. And it's going to keep going until, again, the sensor sees white.
Okay, great. And this is going to be a very simple turn. So in terms of math, all you have to do in terms of understanding angles is that simple 90-degree angle.
Yep.
For now. But
Right.
then we'll get to the next complicated part of the course. We have to navigate a curve instead.
Yeah. So this time we're using the gyro sensor, which is actually going to... what's the word I'm thinking? Oh no, it's gone.
It measures.
Yes.
Right.
It measures the distance, or it measures the angle that the robot is turned.
Okay, got it. All right.
Let's try it.
Okay. Notice that one of the things that's important here is the ability for Mike and I to interact and try this as adults, right, as educators. And so, you can't just hand these robots to teachers and expect them to do amazing things with them. They need the same kind of experiences and challenges that we've now set for ourselves, where we're saying, all right, let's make a track, let's see if we can navigate the track, let's understand how the different sensors work. So if you're doing any kind of robotics work with elementary teachers, they're going to need this hands-on playtime, right, to figure out how this stuff works. Go ahead, Mike, you can set it going.
Okay.
All right, Mike, so this project is skimmers, right?
Skimmers, yes.
Okay, so what do we got?
So this comes from World in Motion, but it's heavily modified for what we do. So you can see there's a pattern for your hull. So basically a skimmer is like a boat. And we're going to try and slide it along a surface with a fan behind it. Okay? And so there's this hull pattern you can use to cut out, but then we need to somehow capture the energy of the wind. Right?
Mm-hmm.
And so that's what we're going to work on. How do we capture the wind? And again, just like the other things we've done today, it's about materials. We're going to put lots of materials out, let students make the decision on what they want to build, what shape it's going to be, how they're going to attach it. And the point of this is to try and get your skimmer to go from one end of the course to the other in as straight a line as possible. And our course today is sort of treacherous because you can fall off either side. So we want them to think like they have passengers, right? We don't want your ship to fall off a cliff, so to speak. Right? We want to go straight and want a smooth ride for the passengers.
Okay, right. Okay, got it. Or maybe you're on a narrow river and you don't want to crush yourself against the sides of
Right.
a canyon or whatever.
Exactly.
Okay, so what are some of the materials we have available?
So we have note cards. We have the card stock that has the whole pattern on it, which you could cut the whole pattern out, or you could do whatever you want with this side. Right?
Okay.
We have some yarn, whatever you want to use that for. We have empty cereal box, so here's some material that can be used easily. We have tongue depressors. We have kitchen skewers. We have straws. We have a number of things.
Tape,
Yes,
scissors,
lots of tape.
paper clips.
Paper clips. So generally, what we do the paper clips are the passengers.
Oh, okay.
So we put 3 of them in there. Great. How about 8? Can we get 8 across?
Okay.
Can we get 10? How many passengers can you carry?
Cool.
right? And we could add some economic stuff in there, right? You get paid so much for your passengers, materials cost so much. Are you making a profit? So
Oh, I like
we
it.
do a lot with this.
Okay, interesting. I like the economic part. All right, let's make some skimmers.
Sounds good.
Okay, so at the beginning of the skimmer exercise, I'll usually take a example, which is junk, right? No one in their right mind would copy this.
That's 2 index cards and a straw, right?
Exactly, and some masking tape and scotch tape here, right? So I'll take this and I'll run it through the course so students get an idea of what we're shooting for, right? But I don't want to give them any ideas how to make theirs, so I make sure that, it's this, right?
This is the terrible version.
So I'll just lay it down in front of the fan. And turn the fan on. And it does go remarkably straight. And
Other than
no further.
spilling a few passengers.
Right. So there's, I'm sure some people are still clinging to safety on it.
Okay, Mike. So tell us about what kind of skimmer designs we see from kids and how you might run this.
Okay, so when it's wide open like this, you see such a variety of skimmers, all shapes and sizes, right? And some kids are going to pay a little more attention to data and what the skimmer's doing, and others are going to go more for an aesthetic value to them. And I've done this before at STEM camps. When I do it in my classroom, though, I like to have every kid make just a basic skimmer and run it.
To start.
Yep, and take some data from that. And then once they've done that, then taking that data and thinking about, okay, how can we improve upon that? How can we change our design so we can capture the most energy from the wind? So,
Okay. So so let's talk about that for a minute. So the learning purpose of this activity is to help kids understand what.
well, you have drag and friction, right? So part of it is what materials are going to have the least amount of friction with the surface you're trying to push them.
okay.
Right? I mean, if we use like rubber material, not going to move anywhere.
Okay.
If we use, this hard stuff, that's pretty good. Maybe there's something better, right? So that's part of it. And then with drag, how much is the wind going to slow us down? And really, how much can we capture that wind is the big thing. What kind of design should our sail be in order to really propel our skimmer the best?
Okay. Could
That's
you
some of it.
right? Do you do like races? Could we time these?
Absolutely. Yep. So usually what we do, we can race them or we can time them going a certain distance. We can measure how far they can go. So for how long can they continue to capture enough energy from the wind to propel their skimmer. And then finally we can do passengers. So we can see how many passengers they can carry a certain distance. So there's really 3 aspects of what we can do when we get to that point.
Okay. Got it. Okay. So this is the inaugural run of USS McLeod, and there we go.
With Lucas, this is what I would show him. Okay, so here's his skimmer run.
Right. Such a goof. All right.
So turn it on. It's sliding. And I would show him, look at your sail, especially when it comes to kind of a stop here. See how it's both sides. I mean, you're losing a lot of energy there. So what could we do to make that more rigid, right? To capture more of that wind energy. Right? Because now you can see the wind's getting there, but we're not able to capture enough of it
Right.
to
Right.
overcome.
Because it's pivoting left and right and
Right.
dumping wind off the side.
Right.
Okay.
So that's so important. Is we built it. We're going through the engineering cycle, great, but we need some questions to help us kind of think of the solution or design pieces we need to get to that goal.
Right. And in fact, so a question might be, so notice that when your sail tilts left or tilts right, what do you think happens to the wind when it does that?
Right.
Which is different from notice that when your sail tilts left or tilts right, you're
Exactly.
losing wind power.
It's all about the way
Right.
you ask those questions.
Right.
It's going to get them
Yeah.
to that
Okay.
next point.
So you want to ask very carefully targeted inquiries that get kids to think about what's happening with my skimmer,
Right.
as opposed to you telling them what's happening with
Exactly.
their skimmer.
Yeah. We don't want to tell them any answers. We want them to
Right.
come upon those on their own.
So what we're doing here now is that Mike and I took my skimmer and we put it just against a solid background, so we had nice sharp contrast.
Yep.
And then what Mike did was that he took a picture of it in an app that's called
It's called Force Effect Flow.
Force Effect Flow.
Yep. And I believe it's from Autodesk.
Okay, got it. All right. And the goal here is that this is basically a wind tunnel app,
Yep.
right? So then, Mike, after we took a picture, talk about the lines you drew.
Yep, so once we had the picture, then I just took the line tool and I drew line where his sail was and then where his hull was as well.
Okay.
Right, and this is from the side. And then I just hit the play button and I select smoke over here and it's going to show me the smoke lines.
It's going to show where the airflow is piling up behind the sail, right?
Okay.
And I can also do pressure, right? So the red, that's where the pressure is building up, and then the blue would be where there's less pressure or the low pressure areas.
Okay, so now if I'm an elementary kid, that looks cool, but it doesn't really tell me how to redesign my sail. Or maybe it does, and I just don't know.
Right, so when you do the smoke lines, especially, you can kind of see where the airflow is going, and you can especially see where there might be air that you could be capturing that you're not capturing.
So like up top, where there's more air up there that's
Right.
escaping over the top.
So you just have kind of a straight line sail, right?
Right.
So
you had a
we
low
could,
profile so it wouldn't tip over.
Right. We could also make the argument that if it was curved a little bit, we might be able to capture more of that wind
Yep.
pressure, right? And we could also do this from the top of the skimmer and get an idea, across the skimmer.
Okay.
If there's more pressure on one side than the other, that could explain why we're going off to the left or right,
Oh, I see. Okay.
right? So we can get kind of two different perspectives on the integrity of our
Oh, right.
skimmer.
Got it. Particularly because my sail slants.
Right.
Okay, so can you pull up that other diagram that you showed me before of that previous
Yes.
skimmer? The one that had 3 sails, I think you showed me? And let's just show our readers that.
That was it.
Yeah, that's it. Okay.
So here's a skimmer from a different time. So I'm going to hit play here.
This is a 3-sailed skimmer.
And it's on pressure right now, right? I'll go back to the smoke. So you can see the 3 sails right there. There we go. So you can see that first sail is the one that really harnesses most of the wind energy. And the next 2 a little bit. If I go to pressure, right, you see there's that red that's piled up against that back one. And then there's almost like a low pressure or a vacuum here
Right.
afterwards.
Right. And okay, got it. And then you can see there's a little push at the back and what looks also like a little bit at the front
Yep.
for whatever that is. All right, cool. So again, you can see the vectors of the flow and the energy push and so on. Okay, Lucas, you made some changes to your skimmer. Tell us about them.
Yeah, so I added just these because I thought they would help keep it from tipping over since it was falling towards the front and the sides. So I put like little rods to keep it stable there, and then I added this to keep passengers from falling off.
Oh, we're going to fall out. Got it. That's a passenger containment device.
Exactly.
Okay, got it. Am I correct that your sail is now leaning forward rather than backwards, or is...
That was accidental.
Oh, that was accidental. All right. Okay, so we're going to see what happens.
We
I
add some white
forgot to
to
get
it.
my passengers.
Oh, you got to get your passengers. Okay, got it. So we need some paper clips. Look at that. Nice.
Yeah.
Good job, Luke. Okay, Mike, so we're having fun with skimmers. Let's talk a little bit about sort of more content subject learning here, right? Not just the building part, because the building's fun.
Right.
We want to attach it to some learning standards and outcomes.
Right.
All right, so math.
Yeah, big one in math. So if we just throw together these skimmers, right, they might work. We might get lucky, it might go straight. But if we start to add some measurement into this and make sure things are balanced as far as measuring out, make sure the sail isn't way lopsided, measuring the materials, we're going to have a higher success rate, right?
Okay,
So definitely measurement's a big
Right.
piece.
So we can introduce students to concepts like parallel,
Right. Parallel,
congruent-
symmetry, things like that.
congruency,
Congruency, yep.
right? Maybe some angles, basic angles, depending
Absolutely,
on the age,
yep.
right? In terms of deviation from straight down.
Yeah, we can test like if you have an angled, if your sail is curved, what would be the best curve to catch the wind the way you want to, things like that.
Okay, got it. And then all of the kind of stuff we've been talking about with some of these other things in terms of rate and distance and
Exactly. Yep.
speed or whatever.
Yep. So
Okay.
time concept.
All right. Science.
Science. Well, we talked about drag. We talked about friction. Friction's a big one with this. Momentum. We can go through like velocity, things like
Right.
that. So there's quite a bit of physics we can get
Right.
into.
Some
And we're
acceleration.
going to call it physics in elementary, but it's physics concepts that we're going to hit with this.
Right. And I loved when we were talking talking about and using the app, right? The wind tunnel app.
Yes.
And you could switch from the smoke to the force, right? And this idea of wind as a force,
Right.
right? Something that pushes, right? And
Yep.
and that was cool because you could see that very clearly in
Yes.
the app.
And in elementary, we talk a lot about motion and force and energy. Those are
Right.
in quite a few of the grade levels. And so this is another activity that can really access that kind of learning.
Okay. And then you said that you mentioned this briefly, and I want to bring this out a little bit, is that you have sort of this, the economy side of things, and attaching
Yes.
some sort of spending concepts to this.
Yes, that adds kind of a real world element to it. Is, you know, if you have so much money to spend, what are you going to buy for materials, right? How are you going to construct it? How are you going to test it so you don't waste your money buying materials you don't actually need? Because if we leave it wide open, kind of like we did today, you know, you can use all the materials you want. You can make a gigantic skimmer, right? But if you're given kind of a ceiling for an amount of money, amount of classroom money you have to use, then you have to start making some choices, some decisions. And as you collaborate in your group, you're going to have to make those decisions together.
Okay, and I think you said something about also like passengers could bring you revenue, so the more passengers you can successfully transfer.
Right, get a little deeper and say, okay, you're going to set a ticket price, right? So how much money can you make with your skimmer, right? And of course, you don't make any money if you don't get your passengers from point A to point B,
Right.
right? So how much money are you going to make? How many tickets can you sell or sell and still
Right.
sail your skimmer across, right?
Okay.
And are you going to make a profit, or did you
Right.
spend too much building your skimmer?
Could you build in like sailing insurance into this, where students would have to
Yeah.
figure out whether or not they have to pay for insurance policy?
Yes, I love to get deep with the economic stuff. So you could, yeah, you could have different sailing companies. You could, you know, get into stock market stuff. And
Okay. All right.
You
So,
get
so
crazy.
lots of fun options around
Yes.
math and science with this. Okay.
Absolutely.
Cool. All right. So that's skimmers.
Yep, skimmers.
Thanks.
Yeah, the fin's really. Come on, Elliot.
I know, but when we get should we put our name, our thing's name on one of the pieces of tape? Oh, no. Yeah, we're gonna.
Heads up, heads up.
Well, with our fins, we had like three fins. We had like three fins, and these two were big, and then we cut like we had big fins and we like cut it in half, and these two were cut in half, and we had another one that was these size, and then we cut those in half and just have this, and then we have it like all four because they like balances every place.
Okay.
And then
So you
she
had
just
two
did
sets of fins there. Two were smaller, two were bigger, right? Thinking maybe do that differently
And
next
they need
time.
to be across from each other.
Okay. Ah, okay. So they're not like symmetrical. They're not on opposite sides perfectly. They're a little off. Is that what you're saying?
No, they have to be on opposite sides. It can't be like this thing's gonna be like that, and this is gonna be.
Oh, they do need to be on opposite sides.
Yeah.
Okay, that's what you're saying. Okay, good, good. Next group.
He said they have to be on opposite sides to help it go up better. It also helps it be more balanced.
Okay. So that, it sounds like that's important, right? Opposite sides.
Okay. So in this segment, we're going to talk rockets, right?
Rockets. Yep.
Okay. What do we got, Mike?
So we have the materials to build straw rockets. So we have straws, and we're going to use these as the launchers. Okay, so to build this, pretty simple. We're going to take a straw and a piece of plain paper, right? And then we're going to roll the paper onto the straw, right? We want it to be a little bit loose,
Not too loose. But
not too loose, right?
Just so that it'll.
We don't want to use the whole piece of paper, so we're going to cut that off and tape it. Okay. So now my straw rocket is just a little bit bigger in diameter than the straw launcher.
Okay, so you've got a paper cylinder that's slightly bigger in diameter than the straw itself.
right.
We'll have to get some different scissors than ones that are gummed up with masking tape.
Yes.
Okay.
So I'm going to roll that. I'll tape it. Okay. And then I'm going to take some of this modeling clay and I'm going to create a nose cone to stick in one end. Okay.
Okay.
And then we'll launch it and see what happens. And from there, we can build fins with cardstock, or we've got some balsa wood here. We have some plastic material.
We might get some fabric.
Right.
Or
So we want to give students
Paper.
lots of options for what they could build. Okay? And maybe we'd give 4th and 5th graders more options than kindergarten, 1st, 2nd grade. But certainly we can make this activity accessible to everyone.
all right, but we're going to start without fins because we
Right.
want to see.
We just want to see what happens when we build a very basic rocket.
Okay, got it. Okay.
An area should also be marked off for launching the rockets. This will make it easier to collect data and make observations. The students could be entrusted to do this, which will be a good way to incorporate measurement.
Okay, all right. So now we're going to put these into action. Okay, so now here we are. We're testing out our initial rocket designs. I'm at the 30-meter mark.
30 feet. We went back to feet.
Oh, we went back to feet. Oh, I thought we were doing metric. Okay, so I'm at the 30. Yeah, all right. That makes more sense. All right, I'm at the 30-foot mark, and we're testing out our initial designs, and we'll see what happens here. Okay, so Lucas, give it a launch. All right, see if you can hit me. Not bad, not bad. Looks like about 20, 21 or so. 22, yep. All right, Mike. All right, and as you can see, that went past, it went past or about at the 30-foot mark. Okay, cool, got it. So, Mike, we just did our initial launch, and as you noted, your rocket, as it got near the end, started wobbling a little bit, right? Lucas's also kind of did a quick nosedive down towards the floor.
Yep.
All right, so what are we talking about with students at this point?
So, a big thing is if you can record when this is happening, then we can play it back. Because when they first launch it, they're not going to remember exactly what it did, but if you can show them that on a video, that's very powerful. And so in our case, both of our rockets kind of lost stability the further they went and started to wobble in the wind. So we can talk about, what could we do to our rockets to make them more stable? Right?
Okay,
And
and
so then we can kind of guide them towards,
Right.
we need some fins out there.
okay, and students might not know, but you can start to ask them to think about, well, what about rockets that you've seen?
Right,
Right, like how do they look different than yours?
right,
Okay.
cool.
So once we launch that, now we can collect some data, we can talk about what we saw, what the rocket did, and now we can take it to the next step and start making it look more like a rocket by cutting out fins. And we have some cardstock here, but really, we want to lay out any kinds of materials the kids might make fins out of, right?
Tinfoil, fabric.
Tinfoil, fabric, cardboard. We do have some like balsa wood here if you want to get crazy.
Okay.
There's this plastic stuff.
Like pieces of metal.
If you have something to cut it with, sure.
Tin snips.
Tin snips would be great.
First graders
yes.
and tin snips are a good mix, I hear.
Yeah, we got some tape. We have these file labels. Who knows, right? So we don't want to
Oh, like
limit
those
them.
adhesive
Yes.
tabs that you put on a file folder to make it like a. Yeah.
Right. So a couple of these on a straw that might work.
Yeah.
Okay. The big thing is we don't want to limit kids by putting out
Okay.
a few materials. We really want them to kind of fly with
Right.
us.
Okay. So like this ball of string. Like we don't really know how the ball.
No
of
idea,
string-
right? But little Jimmy might say, "Hey, I know what I can do with that," and his straw rocket might, break the window. Who knows? I mean, that.
So we've got some tail fins on a couple of our rockets. You can see that I've gone with the green and gold William and Mary theme here. Mike has gone with how many?
4.
4. Okay. And then Mike, talk a little bit about what you just told me about how the fins helps us learn some math.
Right, so we can get some basic fractions, right? So if we're going to put 3 fins on, each fin needs to be a third of the way around the rocket, so they're spaced out evenly. And we can talk about why would we want that on a rocket. We can even make rockets where they aren't spaced out evenly and then see what happens.
Okay. All right. And with older kids, you could get into degrees of a circle,
Right, yep, and get some of that deeper geometry.
angles and stuff. Okay. Got it. All right. And Lucas is working on his fins as well. And he's working on cardstock fins, and he's not quite done yet. We'll catch up with him at the next launch. Okay, so now this is round 3, right? And Mike, we're going to test out your design with the nose cone and the new fins attached to it.
And the new fins.
All right, I'm well past the 30-foot mark. We'll see. Nice. Okay, so a little further, and hopefully more stable. All right, Lucas, you want to give yours a shot? About the same? Okay, so Mike, this is fun, right? We're playing with clay, we're playing with fins and straws and paper and whatever else we decide to do. But, you know, it's easy to get consumed in the task again, and the focus is on the rockets, not on the learning. So how do we make sure that there's some learning happening here?
Yeah, you're right. It is fun, but we can focus on data, so we can collect distances, we can weigh our rockets, we can talk about drag, right? So as these are moving through the air, what's slowing them down? We can talk about gravity. So there's a lot of science content we can encounter there too.
Okay, and at an early conceptual level, because these are elementary kids.
Right.
Right. Okay, got
On
it.
top of that, we have collaboration. We have those soft skills we talked about.
Okay, so just we want to make sure that the STEM or STEAM is in this, and it's not just woo. We played with rockets today. What'd you learn? I have no idea.
We
Right.
definitely want to be collecting data as well.
Right. So something beyond. So we want the learning to extend beyond simply making the rocket itself.
Right.
Okay. All right, Mike. So now we've got a different kind of rocket. So what are we doing now?
Okay, so we're dealing with a water rocket here, and these are the dollar store water rocket, right? You can find these just about anywhere. These are fantastic for isolating a variable. There's not much to this. We're not going to do any real construction on this like we do with the paper rockets, the straw rockets. So there are two things that kids can manipulate here. One is how much water we put in the rocket, right? And younger kids, we might just kind of eyeball it when we put it in and say we have this much, and the next time we try more.
Okay. Or
right?
we might put a mark on there or
We might
something.
put
Yeah.
a mark on there, exactly. Older kids, we're going to use maybe a graduated cylinder and measure out how many milliliters, and then use a little funnel to put it in.
Mhm.
Okay. But also, we can measure how many pumps we do. Okay. So when we do this with kids, we might put in the same amount of water each time, and then change the number of pumps,
Okay.
right? And then measure how high it goes.
Got it. All right.
Now,
So-
for us today, we have an altimeter we're going to attach to it, and the altimeter is going to give us back some data about height, velocity, things like that.
Okay, so if you don't have an altimeter, how would you measure height? Because that's your dependent variable, right?
Right, so you need some kind of reference point, right? So even right here on the building, we have these bricks going up, so we can count how many bricks high it went, right? Things like that.
Okay. Okay, so Mike, we forgot our graduated cylinder, so how are we going to set this up?
Right, so we're gonna dump it in here, like so. I'm gonna wiggle it around. I can see the bubbles coming out, and when I pull it out, I can mark that on there. So this is how much water we did for trial one.
Okay.
And we can focus on doing pumps. So each time I fill this, I want to fill it to that same line, so that that's a constant.
Yep.
And then we'll record how many pumps we do.
Okay, so let's do that. Okay, so Mike, we're wrapping up the water rocket experiment, which was
Right.
sort of a failure today.
It was.
So what's going on?
Well, the altimeter wouldn't work, but that's okay. We can still collect data in other ways. And I especially just like that activity because it's easy for kids to isolate a variable. And so I used it at the beginning of the year to talk about how we do science. And so we talked about having a variable and testing that variable and having to isolate one thing in your experiment so you know what effect it has.
Okay, so again, just to remind everybody, we could have isolated either the number of pumps or
Yep.
the amount of water. And it doesn't matter that the altimeter didn't work. We could use a rough approximation like
Right.
the side of a brick wall or something like that.
Yep.
Okay, so we're hoping that our altimeter works better with our next rocket,
Right.
which is a more advanced water rocket, and
Yes.
that's where we'll go next. But lots of rich opportunities for data collection and analysis here, hypothesis generation, and to have young children start to think about what does it mean to think like a scientist, to collect data and so on.
Yep.
Okay, cool. Okay, Mike, so this is another water rocket. So what do we have?
Okay, so yep, it's a little more advanced, but it also builds on some of the straw rocket stuff we did. So we're taking just a regular empty 2-liter, okay, and we're going to make it into a rocket. And to do that, we could do much like we did with the straw rockets, where we could just take the 2-liter itself, put a little bit of water in it, stick it on the launcher, launch it, see what happens.
Okay.
So after we would launch it, it's not going to do very well if it's just the 2 liter by itself. So then what do we do to make it more like a rocket? And just like the straw rockets, we're going to add some fins. We put a little bit, you can't see it, but there's actually a washer up here, a couple washers to add some weight. We tape those on. We could go even deeper than this. We could make nose cones.
Okay, so what does the weight do on the other end?
The weight's going to add to the stability of the rocket.
Okay.
And just a little more force.
Got it. Okay. All right. And
Set
then,
it on like this.
all right, and then like the $1 bottle rockets that we got from the dollar store, same principle. We're going to fill it up part way with water, and again, we can isolate a variable here in terms of amount of water,
Right.
right? And what else? What are other variables that we can play with?
Fin size, material.
Okay.
We can go with any of the pieces we build on the rocket. We can talk about
Okay.
material,
All right.
size, shape.
Okay, now you've got a launcher here, and it looks like it has a gauge on it.
Yep.
And what does the gauge measure?
PSI, so pressures per square inch.
Okay,
Pressure
so
per square
all right, and is that a variable that we can isolate on?
It is, yep. So
Oh.
one more variable.
Okay, so this would be the equivalent of number of pumps.
Right.
In this case, we would be PSI instead.
Yep, a little more accurate measure of that.
Okay, got it.
Another rich activity.
All right, let's see what happens.
Okay.
Okay, Mike, so we had a very successful soda bottle rocket launch, right? How high did it go?
136 feet.
Very nice, very nice. And I lost it in the sun there for a little bit, but I think I caught the end of it coming back down on the video. So let's talk a little bit about equipment. I mean, you talked about sort of the soda bottle rocket and, the weighted end and the fins and stuff, but we didn't really talk too much about this stuff.
No.
So show us what we got here.
Okay, so obviously first you need a pump. And so this is just a basic bike pump. You can also purchase these with a gauge on them. Okay, and so
So that shows you the pressure gauge with a PSI.
Yep.
Okay, pounds per square inch.
So this is a homemade launcher, and it's made from parts that are from the hardware store. So if you see underneath, right, it's mostly PVC, and then we have some different pipe pieces, and then of course we have the gauge, which is that all-important part.
Okay. Now, most people maybe don't have the skill to make their own launching base,
Right.
right? So tell us about this thing here.
So this is from Pitsco, and it's another kind of launch base.
PITSCO.
Yep. So it comes with So the bottle would go onto here, like so.
Okay, and here's the end that would go to the pump. And again, it's kind of an ordinary bike pump.
And then go in here, something like this. And these clips come up here.
And then you stick this thing through the base.
Yep.
That holds it all tight
Pump it up,
and has
and
a
when you're ready,
really long string.
yeah, which is probably good since this one's very short.
Right, and so then when you pull this string,
I'm
this
gonna release these
the clips come loose and off it goes. Okay, cool.
without this in it.
Right. Okay. So, diet soda 2 liter bottle not included.
Right.
Okay, gotcha. All right. So, and then we got the altimeter to work well.
We did, yes.
On this one, which was nice, which gave us something else to graph as a dependent variable. And like the water rockets, the basic dollar water rockets, right?
Right.
A way to teach kids about graphing and data collection
Yep.
and hypothesis testing.
Right. Yeah. Along with some basic science content like pressure and potential energy is a big one you could use in there too. So it just depends on what your science
Right.
content is.
Well, one of the great things about this one was that because it went up so high, and then we had even just a very light wind today, but it drifted.
Right.
So we had to sort of estimate where was it going to land,
Yep.
and why did we think it was going to land there, and all that. So that was good stuff too.
Yep. So some of this could be done ahead of time, as we make predictions about what's going to happen. How high is it going to go? Why do we think that? Where's it going to land?
Right. And obviously, as you work with older students, you could even get into things like, graph the path of the trajectory
Right.
and so on. So lots of cool stuff you can do.
Yep.
Okay. Cool. Thanks.
This was really fun.
Right. And so, Mike, tell our viewers what you're doing next week.
Okay, so next week we're doing NASA STEM. We'll be shooting rockets off, but one of the activities we're going to do is called Eggonauts, and we'll take 2-liter bottles like this, but then we'll build a capsule on top, and we'll put an egg in there, and we'll launch it and see if kids can land the egg without cracking it.
Okay, and the egg's just going to fall down on the ground. You hope it doesn't crack.
No, I mean, we're going to do parachutes, there'll be a capsule, they'll have to think what material you want to put in the capsule to cushion the egg. So
Okay.
there's going to be lots of opportunity to make decisions and,
Okay.
and engineer. So.
Okay.
3, 2, 1.
All right, let's check.
I think Buzz made it.
Let's see.
He made it.
Success!
Success! Success! I didn't let it go at the right time, otherwise it would have been.
Okay, Mike, tell us what we're doing for this project, what it's called, what the basic idea is.
Okay, so this is called Thrust Wars, and the object is to create some kind of balloon-powered vehicle that will go from one end to the other. And we're
Okay.
looking for speed. Well, first of all, that it gets there, and also how fast does it go, and then can we carry passengers with it?
Okay, so explain the setup here. So you said from here to there, but
Yeah, so we have 2 chairs set up. We have a fishing line in between.
Okay.
There's a fair amount of tension on it.
all right, so kind of like it's tight like a tightrope right now.
Right.
All right, Mike, so what do we have to work with here?
All right, so first of all, we have balloons, and the more sizes, the more shapes you have available, the better, right? Because that's that's gonna be a great opportunity for critical thinking. What shape of balloon is the best to power our vehicle? What size? How much do we blow it up? Things like that. So the more balloons, the more shapes, more sizes you can have available, the better, right? We also have balloon pump. This can be used, right? Because now we can count. Okay, so I pumped the balloon out 8 times. So we record some data that way and then look at the results and how that
Okay,
affects.
where do you buy a balloon pump?
This we bought at Walmart.
Oh, all right, got it.
Pretty much anywhere we're gonna get. And I think it was, I don't know, $2.
Okay, nice. All right.
It was found with balloons. We have straws, right? And with all the other activities we do, I don't want to say, okay, so kids, you can take the straw, you're going to cut it, 2 inches, and you're going to attach the balloon and you're going to shoot it. No. We're going to put these out, right? And maybe they use it to guide their vehicle down the string. Maybe they use it for something else. We're going to let them do that. We're just going to put it out and make it available. Same with paper clips and these things that I don't know the name of.
Binder clips.
Right? And we have tape. Right, and really, we'd say anything you can think of that's available to you, we're going to use. We got paper out. They might not use this. Maybe they use it for something I never
Okay,
thought of.
so just a range of random materials.
Exactly.
Maybe like pipe cleaners or whatever.
Yep.
Okay, got it.
Come on, go! You can do it, Balloon! Come on!
Well, the balloon made it. Okay, so this is a great opportunity to add economy into your project. So in this case, right, we told the students, participants, you have so much money to spend, right? We give Monopoly money or Game of Life money, whatever, and they have to purchase their materials, right? Well, then they can set a ticket price for their passengers, right? So, for instance, if Colin here can get 100 passengers across, each one is $3, he makes $300, right? So that can offset the costs of building his colossal vehicle, right? Whereas Gabby might not spend a lot of money constructing hers, but she might only be able to carry a few passengers across. And we can have those conversations about opportunity costs, supply and demand, and things like that.
All right. Thanks for joining us today as we took you through some different STEAM activities, from rockets to skimmers, from balloon wars to
Robots.
robots. Yeah, I forgot about robots. And please get in touch with us if you have questions. We'd love to talk more about STEAM, STEM, and everything in between. Ready?
Hope we gave you some ideas to put some bang into your elementary STEAM activities. Man, that was really bad, wasn't it? Okay, sign them off.
2 more balloons?
Thanks much. step back.